Hi there, welcome back. This is lesson 6 in our organic chem unit. Today we're going to be answering the question, what are isomers? So what makes the most sense for this lesson is to follow along with the note sheet that is titled Isomers. And this is structured very much like the drawing and naming hydrocarbons lesson. There's a lot of built-in practice. I'll show you how to do something, we'll practice it, add something to it, practice it, add something to it, practice it. Tomorrow there is more practice on isomers with like regions questions. So if you're still a little bit confused at the end of this, that is totally okay. Looking at the homework post-it, it doesn't look like there's anything due tonight. Just make sure that you are following along to the calendar as well as whatever other announcements your teacher gives you. So getting started. On the top of your page, there's the yo-yo. I didn't give you space to do this, but if you want, take a second or a few minutes, however long you see fit, and see if you can figure out how many different structures you can draw that each have the structure, the formula C5H12. So using only those pieces, only 5 C's and 12 H's, how many different compounds can you make? So take a second, pause the video, try that, and then when you think you have some, come back and we'll talk about it. So today's topic is isomers, and you might be thinking, well, what are they? And the textbook definition of an isomer is the compounds with the same chemical formula, but different molecular structures. So it has the same pieces, they're just arranged differently, okay? So if you had, a box of Legos that you buy at a store, you can build an infinite number of different kind of creations using only those pieces. Those are what isomers are. Same compound, same formula, the same pieces, but they're arranged in different ways. So you might notice that it says iso, and we talked about something earlier on in the year with isotopes, and those were the same element but different versions of them because of different masses. If you think of an isosceles triangle, I'm not even going to try spelling that, but that's a triangle with the same side on all 3 sides. So iso, we're talking about something being the same. So same formula, different structure. Now there is a bunch of different types of isomers. We're just going to focus on structural ones. So same formula, different arrangement. Okay. So question. Are these 2 compounds isomers? So if you're not sure, a good tip is to name the compound. So if you name the if you think, obviously these 2 things look different. So, but we have to see if they actually are. So if you're not sure, name them, and then if they have a different name with the same formula, they are isomers. So for compound 1, we have C4H10, and if we're naming this is a very simple straight chain alkane. So we have bute for 4 carbons, ane for those single bonds. So that would be butane. Compound 2, on the other hand, if we count it up, we have C4H10. So we have the same formula, the same pieces, but the name of it, find our longest chain, that's 3. So that's prop. Single bonds is ane. And we have this branch, so this makes it 2-methylpropane. So this is what I was talking about before, where you have the same chemical formula, so the same pieces, but different names. So are these isomers? The answer is yes. They have the same formula, but different structures. Now looking at these 2. Compound 1 is the same compound 1 we used before. It's still C4H10, and it's still called butane. Bute for that 4 carbon longest chain, ane for the single bonds. But now, let's name compound 2. Compound 2 obviously looks different, but if we name it, then we'll see if it's actually different. So if we count up all the pieces, it is still C4H10. So the formula is the same. But we have to name the longest chain first. The longest chain, even though it bends, that's okay, is still 4 carbons, so that's bute. There are single bonds between those carbons, that is butane. So, are these two isomers? The answer is no. They have the same formula and the same structure. So just because it's bent doesn't change it, it's still butane. So that's why finding the names of these things is super important. So looking at these two pictures of Mr. Potato Head, Mr. Potato Head is a great example. So if you ever played with Mr. Potato Head, you get like this potato shaped thing, and he has like a little, he's hollow inside, so you can open up his butt and all these pieces get stored there, and you can kind of use these different pieces. So looking from this compound to this compound, or structure of Mr. Potato Head, would you consider these to be isomers? And the answer is yes, because you have the same pieces, but they are arranged differently. So he still has his black hat, his eyebrows, his 2 eyes, the nose, 2 ears, mustache, mouth, and feet, and 2 arms. But now everything's placed in a different location. Now these two pictures of Mr. and Mrs. Potato Head, would you consider these to be isomers? And the answer is no. They have different pieces. So now, if you have an isomer, you have to be using the same pieces. But when we look at Mrs. Potato Head, now we have a different hat. She has different shoes, she has earrings, her nose looks a little bit different, her eyebrows are different, so there's different pieces. They're completely 2 different structures. So in terms of chemical formulas, the chemical formula would be completely different. So, when we are drawing an isomer of alkanes, again, we have to use the same molecular formula, so that's a given for everything. And a good rule of thumb is to, well, you have to draw a different structural formula. So when you have just these long alkane chains, you can just kind of create branches off of it. So this original compound is, our formula is C6H14, and that is hexane. Hex for the 6 carbons, and ane for all the single bonds. Now, your job is to create 2 different structures, if you can, of hexane. So same pieces, different structures. So if you want, pause the video, take some time to think about it, and then when you come back, I'll show you some examples. So one example that I have is 1, 2, 3, 4, 5. I'm going to add a branch on that 3rd carbon, like that. And again, remember, at the end of every dash, there is an H. We'll just be here forever if I draw every one of them. And if we count all of the carbons, there are still 6 of them. And there is 14 H's. So just in case you forgot, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 H's. So anything that's highlighted in red is an H. So, if we're going to name this, we have to name the longest chain, which is pent. Ane, because we have a single bond between them. And we have this methyl group on the 3rd carbon. So now this carbon is called 3-methylpentane. Same formula, different name, that is an isomer. With number 2, another example that you could do is 1, 2, 3, 4, 1, 2, and now each of these green dashes represents an H. Now this formula is still C6H14, and this is named 2-ethyl butane. Bute, because you have the longest chain is 4 carbons. Actually, hold on. This is not 2-ethyl butane. This is actually the same compound as before. So, when you have to name your longest chain, our longest chain right there is pentane. And we still have that 3-methyl group. So this would not be an example of an isomer. So if we erase this one, let's try another one. Let's see, we can do something that looks like this. 1, 2, 3, 4, 6 carbons. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 H's. So we still have C6H14. But now our longest chain of carbons is 4. So that's bute. Ane, because we have the single bonds. And we have these 2 methyl groups hanging off of it. And that would mean we have the 2,2 dimethyl butane. So you have to make sure that you are really checking these longest chains, because just like I made that simple mistake bending it, you can too. So that's why when we draw it and then we name it, that's kind of your check. Okay. Another example is for these alkane isomers. We have this compound, and the formula is C4H10, and it's butane. Now, one of the examples of an isomer is 1, 2, 3, like that. See? And then each of these blue dashes represents an H. The formula is still C4H10. And if we're naming this, this is named 2-methyl propane. Now, this is an isomer, so we can give that a check. If I draw this, though, so if I draw 1, 2, 3, 4, and have all of my H's in green, I still have C4H10, but when we're naming this, your longest chain is still 4 carbons. That is butane. This is not an isomer. Okay? So it does take some trial and error, and you have to just kind of, as long as you're naming it at the end, that is a good check. Okay. Last example. Again, I'm gonna go through this a little bit quicker because now we've done this a few times. This formula is C5H12, and it is named 2-methyl butane. So when you have a branch, one of the quickest ways to make an isomer of that is just to create the long chain, straight chain of this. So you have our 5 carbons, and then everything in green is an H. We still have that C5H12, and this compound is named pentane. Another example of one would be this. 1, 2, 3, 1, 2. So creating that cross shape kind of thing. And now everything in orange is an H. We still have the formula C5H12. And this is named 2,2 dimethyl propane. So again, you can add all we did was take this and move it there to create the last isomer. And then to create isomer 1, all we did was take this and pop it at one of the ends. Okay, so next main section is creating isomers with alkenes and alkynes. So adding things with double and triple bonds. Now the easiest way is to just change the location of that double or triple bond. So there are more options that you can do, but the easiest way is just to kind of move that bond. And I'll show you what that looks like in a second. Okay, so looking at our original compound, our formula is C6H12, and we're going to name it 3-hexene, because our longest chain is 6 carbons, and this triple bond starts at, the, third carbon, and we have that YNE ending. Let me just clear that up a little bit, because of that triple bond. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10. This is hexine. Now, and we have it 3 because it's like that. Now, if we wanted to draw an isomer of this, we can still have 1, 2, 3, 4, 5, 6. Your 6 carbon chain. And let's just move that triple bond somewhere else. And then everything in green will be an H. Now this formula is still C6. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's. And the name for this one would be 1 hexine, because now this triple bond starts at the first carbon. One of the other examples that we can have is 1, 2, 3, 4, 5, 6. Let's put the triple bond there. And now everything, I'll connect these. And now all these orange dashes are these H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we still have C6H10. And now this would be named 2 hexine, because we still have the longest chain of 6, but now that triple bond starts at carbon 2. Remember, you have to label it as the smallest number. Now there are more possible options. This is just to keep things kind of simple. Okay, next compound, we have this. The formula is C4H6, and we're going to name this 1-butine. But because we have 4 carbons, ine because we have that triple bond, and 1 to show you where that triple bond starts. Now, what we can do is draw something that looks like this. And now every other blue dash is going to be an H. We still have C4 and 6 H's. But now this compound would be named 2-butine. But because we have the 4 carbons, ine because we have that triple bond, and 2 because that tells you where the triple bond starts. Now just bear with me for a second. If I show you this compound, 1, 2, 3, 4, and now everything in green is an H, we have C4H6, but this is still 1-butine, because all we did was take this and flip it and make it the mirror image. So when you're naming this is still you're adding triple bond to the smallest number, so that's still carbon number 1. So this example is not an isomer. So some compounds have more isomers than others. It just takes some time to kind of fool with it and play around with it. Okay, last example for this section. This compound is C5H10. So we have 1, 2, 3, 4, 5 C's, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, hydrogens rather. So this would be named 1-pentene. Pent because we have 5 carbons, ene because there's a double bond somewhere, and 1 tells you where that double bond starts. So if I drew something like this, 1, 2, 3, 4, 5, and now all of my H's will be green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We still have the formula C5H10, but now this is named 2-pentene because the double bond now starts at carbon number 2. So this is why it's so important that we are naming where these multiple bonds are. Now, if I draw something that looks like this, 1, 2, 3, 4, 5. Now all of my H's will be in blue. 1, 2, 3, 4, 5, 6, 7. Actually, let me do it like this. You still have the formula C5H10, but this is still named 2-pentene. Because I flipped it and now these H's are on the bottom, that doesn't change anything. So this, not an isomer. So that's why once you draw something, going back to name it, that's incredibly important to checking your work. Okay, last example, or last section, is creating isomers with functional groups. So again, our key function, or key goal, is to have the same molecular formula, but a different structure. So a key tip for this is just, if it's possible, you can take the functional group and put it somewhere else, or you can move part of the carbon chain and create a branch. So these are a little bit more challenging, and only basic isomers with these functional groups will be asked. So we're not going to, make you create things that are way too crazy. If you want to try and make as many as you can, by all means go ahead, but you don't need to overcomplicate it. Okay, so for this example, we have C5H10Cl2. Okay, we have these added Cl's right there. And if we're going to name this would be 1,2-dichloro pentane. So pent because we have 5 carbons, ane because we have the single bond between those carbons, chloro because we have a chlorine functional group somewhere, di because there are 2 of those chlorine groups somewhere, and 1 and 2 gives you the location of those chlorines. Now, one of the examples we can do is just take these chlorines and put them somewhere else. So we could go 1, 2, 3, 4, 5. Let's make the chlorines in green. And now everything in red is your H. Now if you're adding something other than H, you have to write the formula. So I can't just put a dash and say, oh, that's chlorine. The dashes only are invisible H's. So if we're looking at this formula, it is still C5H10Cl2. But the name for this one, it's still dichloropentane. But when you give the location of the chlorines, they're now both on carbon number 2, so it would be 2,2-dichloropentane. Another example, and again, there are a bunch more, but I'm only going to stick with one more. Could be 1, 2, 3, 4, 5. Have your carbon chain there. Chlorine, chlorine, and then these blue dashes will represent the H's. We still have the formula C5H10Cl2, but now, and it's still dichloropentane. But with the different locations of the chlorines, it is 2,4 dichloropentane. So changing the locations of the chlorines is all you have to do. Now we could, if we wanted to, make branches off of this, but then the name gets really complicated and you don't need to do that. If you want to, by all means go ahead. Try it and try naming it, and if you want to check yourself, send the picture to me or your chem teacher to check it. Okay. Another one is this. So this is your original compound. Your formula is C4H10O. So we have 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's, and that one O. And we're going to name this one butanol. So but because we have those 4 carbons, AN because we have single bonds between those 4 carbons, and OL is the ending for when we have that alcohol. And 1 tells you the location of where that OH group is. So again, if naming these functional groups is completely foreign to you, go back to lesson 4 and 5 to go over the topic a little bit more. So the easiest way is to take this OH group and push it somewhere else. So we could draw something that looks like 1, 2, 3, 4. Have those bonds. Let's make our OH group over there in orange. And now everything in green will be those H's. So we still have C4H10O. But now, since we moved the location of the OH group, it is now called 2-butanol, because now this OH group is on the second carbon. It is not 3-butanol because you have to use the smallest number. Okay. Now, if you wanted to make things complicated, because who doesn't like adding complexity to their lives, we could draw something. We can completely change this functional group and turn this alcohol into an ether. You might be thinking, how? Well, like this. You could do 1, 2 with your carbons. Put that O in the middle. And this is where the kind of trial and error comes into play. All your carbon chains. And now, everything in blue is an H. We still have the formula C4H10O. And this would be called diethyl ether. Remember, when we're naming ethers, we have, well, even before, backtrack a second, an ether is characterized by an oxygen and a carbon chain on either side of it. And then when you're naming it, you name this branch, you name this branch. And since they're both ethyl, instead of saying ethyl ether, you say diethyl ether. These names are definitely a tongue twister. Now, if you're making the jump from here to here is a little bit tricky for you, that's totally okay. As long as you can get to that is fine. But the ether does, make it a little bit more complicated, and creating all these options, I think, is a pretty cool puzzle. Okay, last example for today is this compound. And so, this is, if you notice, this is still the same formula we were working with on the previous question. So the formula is still C4H10O. And we just went over that it was called diethyl ether. So we can create even more isomers than what we had before. So now, for starting with the ether, one of the easiest ways is to take one of these carbon chains and just put it on the other side. So, to do that, we could draw it as, using all these different colors is so much fun. 1, 2, 3. And then everything in H is your everything in orange is your H. And so the molecular formula would be C4H10O. But now when we're naming this branch is methyl. This branch is now propyl because we have three carbon chains. So it'll be methyl, propyl, ether. Again, pretty much a tongue twister, but pretty cool. One of the other things you can do is completely change the functional group, and we can go back to what we started with the other question and have something that looks like this. So what I'm drawing is what we started with. Formula is still C4H10O, and this is 1-butanol. So again, putting the OH group at the end is the same thing as what we started with the last set of examples, because you're still numbering it with the lowest carbon. So for this example, if working backwards if working towards isomer 2 and recreating that functional group is kind of tricky for you, again, that's fine, as long as you're kind of comfortable going from original to isomer 1. So that's it for today. I know it was a lot, so if you stuck through and watched all of the examples and tried on your own, great job. Tomorrow there is more practice on isomers, and you'll see that most of it is multiple choice questions, and there are some short answer questions, but it's relatively simpler than what we did today. The way I think about it is, if you're able to do the hard part, then the easier questions will come a lot simpler to you. So on that note, that is it. Have a wonderful day.